hypothesis testing. And we're going to do over the next 2-3 weeks, next 3 weeks really, I guess. One of the weeks is holiday. Hypothesis testing of a single proportion, of a double proportion. Hypothesis testing for a single mean and for the difference between two means. Almost identical in the way that we did confidence intervals. Remember the confidence interval 1 and 2, mean 1 and 2, going to do that. A lot of people find this challenging, and that's good because it means we learn stuff. And I think part of it is that the hard part, and then there's an easy part. And the hard part is just getting to grips with the whole process of what a hypothesis test is doing and how you set it up. Because once you can sort that out, for the most part, the easy bit is doing the number crunching. Because for many of the questions, the number crunching is going to be done by SALT, right? So you're going to find that SALT takes a lot of it does a lot of the heavy lifting for us. But setting it up is going to be our problem. And let's begin. And here is a very generic version of the 5 steps that every type of hypothesis testing, and I mentioned 4 today, take. Step 1 talks about finding what's called the null and alternate hypothesis. Step 2 is find a thing, a statistic called p-hat, which we already know how to find, don't we? Step 3, find a new guy, a new statistic called the p-value. And we get that by comparing our test statistic with the null value from the null hypothesis. And then step 4, we make a conclusion. And then step 5, we turn that conclusion into something that sounds more like English. So 4 and 5 are almost together. So let's return back to step 1. We are going to find the null and alternate hypothesis. This structure is very formal. It's been agreed for a long time. Thankfully, statisticians all got together in this one, so we all do it the same way. So if you go to any textbook, it's going to be pretty much the same. If you went to France and converted their textbooks, it would look just the same, right? So everybody in the world has kind of formalized this. It's really a way of saying, is there enough evidence to prove something? That's what a hypothesis test is. Is there enough evidence to prove something? And the way that we do that is that we set up 2 distinctly different, what they call hypotheses, 2 distinctly different things that could be true. And we use notation, H0 and HA. H0 is going to be called the null hypothesis. It's basically the status quo. And what I mean by that is nothing to see here, right? There is no change in the value that you think has changed, right? It's the same value it's always been. Because the way we tend to do these is we say, I think this value has changed. It's got bigger, it's got less, or it's just different in some way, right? And the null hypothesis is nothing to see here. And the alternate is we believe that the value has changed. I'm keeping it nice and vague. In some way. So there are in fact going to be 3 types of null and alternate hypothesis, right? They end up being just 3 kinds. And I'm going to show you those 3 situations by having 3 different stories, one for each situation. So we'll start with the first one. in 1900, oops, 80% of Americans So if you went back to the 1900s and you asked people, are you in favor of hanging murderers? 8% of them believe that, right? So we're going to use that as our foundation. That's basically our null hypothesis. And we would write that down as P, the percentage of Americans who believe that you should hang people for murder, is 0.8. Now, I'm a social scientist, and I believe that that has changed over time. I now believe that less people, right, less than 80% are in favor of hanging for murder. So, is there evidence that it is now less than 80%? If you want to do a less than, you write it like that. So that's my null hypothesis. It's still 80%. My alternate is that the new number for the population, right? So the population has changed, is now less than 0.8. So status quo, nothing changed. Alternate, something has changed. Okay. Now we have some names for these. This guy is called a left-tailed test. Can you see it's kind of pointing to the left from one of a bear? And that's our first one. I said there's 3. So let's try another one. The last election, 45% in a particular state voted Republican. Is there evidence that this year it is now more than that? So, you know, people's political opinion changes, at least in this pretend story. What would our null and our alternate look like? The null is that it's still 45%. The null hypothesis is always going to be P equals a number, right? P equals a number. The alternate depends on what we think might be happening here. When I say, is there evidence that today, this year, it's now more than 45, would you agree that that looks like that? That's called, right? Greater than, right? More than. And if this is called a left-tailed test, what name do you think we sometimes call this hypothesis test? I see your mouth moving. It looked like you're saying right.
Right.
Okay, great. So what I want you to get out of this is a null hypothesis is always going to be P equals a number, and the alternate can be, is there evidence to prove that it's changed and went down the way, or changed and went up the way? And I said there's 3 of them. Right, that's a left-tailed test. That's a right-tailed test. Evidently, there's one more. A country has 25% of its people overweight in the year 1950, at least. And we would like to conduct a test to see, is there evidence that it has changed? Now, we're not specifying how it changed, but that it's not 25% anymore. Because sometimes you don't know how it's changed, but you know it's changed, right? You know it's different, but you're not 100% sure it's different because it's got bigger, or it's different because it's got left. That you'll figure out later when you conduct your sample and do all your number crunching. Right now, we haven't done any of that, right? Right now, we're just at the making up the question kind of stage, right? Thinking about it. Now, in this case, the null hypothesis will be 0.25, and the alternate hypothesis, how do you think you write this last one?
Doesn't equal.
Right. And that's the symbol for that is an equals with a stroke through it. Doesn't equal, or not equal to if you prefer. And this one has a name as well. You want to have a guess at what the name is called when you do the third type of hypothesis test?
Two-tail?
It is. So in one of those three situations is going to happen in any hypothesis test involving a single proportion, right? You're either going to get a null hypothesis, P equals a number, and the alternative is it's changed because it's now less, or that it's equal to 45 is the null hypothesis, or it has changed, but now it became more, or it's still equal to 0.25, right? Or it's changed, but you're not sure which way. Are we comfortable with the structure of what the hypothesis test begins with, right? So I'm just
I have
going
a
to...
question.
Yes, Rob.
Probably a stupid one, but I'm gonna ask.
No,
one.
no, there are no stupid questions.
Why is it called? Why is it called two-tailed?
Oh, well, when you're not equal to it, it comes from the visual. There's going to be a guy later on that we get called the p-value, whereas here, right? But essentially what you're going to do in these questions is you're going to have a normal distribution, right? And when you're looking for something less than 0.8, can you see that if that's 0.8, can you see less would be to the left of it? And if you're looking for more than 0.45, it doesn't really matter where 0.45 is. Can you see why that would be a right? So less than 0.8 would be this kind of guy. More than 0.45 would be this guy. So how would you draw a picture of this last one? Oh, by the way, the number in the middle would be this guy here, right? So if you were thinking this number here is 0.25, if I was saying it's not equal to P, wouldn't not equal to P kind of live far away from the middle? But it could be in the big side or it could be in the small side. It's a bit like it might be this or it might be that. Well, if we call these the tails, you see this has got two tails. So it's two-tail test, left test, tail test, right tail test. So that's where their names come from. So let me put a story down. I'll give you a few seconds to figure it out. Police force believes that during a full moon, they have more crimes. So let's suppose we try and set up a hypothesis test for whether or not you could prove that, right? So a police force believes that during a full moon, they have more crimes, okay? So in January, there's 30 days. And so the probability for full moon is 1 out of 31. You agree? And so let's just make our life easy. I guess I shouldn't really call that P. And the percentage of crimes gets reported is 1%. So on a normal January day, they get a 1% crime rate. Right. On a full moon day. So if we wanted to test, does a police force believe that during a full moon they have more crimes? Wouldn't they simply just say, well, how many crimes do you normally get? And on a full moon day, is that number of crimes bigger? Right? What percentage of crimes are they? Now that I've seen that one, I'm less comfortable with my choice of question. So let me look at some of the homework ones because they're just better. If you try and pick a question off the top of your head, don't always come out quite what you were hoping. Right, so give me a few settings. I'll up this a little bit. Oh, shooting space, come on. Go away, window. There, that's
By the way, that is a myth.
it is definitely not provable. Although I have one of my nieces works in a hospital, and she says full moons tend to be crazier than non-full moons. Whether that's just, that is anecdotal. But she believes that full moons brings out the crazies, as she calls it. But that I've never seen anybody actually prove it. So I believe what you said is true, that it's not. There's no evidence to say that it really is true.
I can prove it.
You can.
I worked law enforcement in the Navy for 6 years. Every full moon, we had an increased number of incidents across the board every year, every full moon.
But maybe the problem is that we haven't collected enough data to get evidence yet. Maybe. Okay, I'm lost here, which is pretty much me normally. Here we are. Are we now looking at question 1? Okay. A previous example. I don't know why that's a previous example because we haven't done it. Any others? Hypothesize that the proportion of babies born during the full moon, so it's a kind of full moon story, is 1 out of 29.53. Interesting fraction. But this is based on the fact that a full moon occurs on average 1 out of 29.53 days. And so we could easily classify as a baby as born during a full moon. So here's a person in the nurse that thinks full moons, babies get born more often than, a Tuesday night or any other day of the week, right? So kind of similar to the crime one that I just did. Now, they ask you questions we should be comfortable with. Oh, darn it, we got the answers, which are a distraction. So let me get those answers out of the way. Are they gone? Are they gone? Yes, okay. So what's the population here? Are you happy that it's all babies? Now, specify the parameter of interest. So in this story, aren't we interested in the proportion of babies born during that time? So the proportion of all babies born during the 24-hour period surrounding the full moon. We're good on that. Now, What would the null hypothesis be here? Well, wouldn't that be P equal? And I wonder if I can copy that. No, I can't. 1 over 25. So it's going to be a little fraction button. 1 over 29.53. Right, so that would be, there isn't any evidence, right? You get born during a full moon just as likely as you get born during any other time, right? They don't have this. It would have been nice. What would the alternate be if you thought that it was actually bigger? In other words, you think more babies are born. What would you write as your null hypothesis in that story? Can't hear you, Rob.
Wouldn't it be the 1 in 29.53 for your null?
Yeah, that's the null one. But what would the alternate be? The
Be greater than.
HA. Greater than, right? Suppose I thought that less babies were born during the full moon, right? Wouldn't I do a P less than that number? And if I said, I don't know what it is, but I know it's different, wouldn't I do the third one not equal to that number, right? So in the storyline, there's going to be, in this case, they didn't have any obvious one, but can you imagine in the storyline they would have that? Now, here's a funny little thing. You can't do the not equal symbol because there isn't one, evidently. I don't know why there's not. You would think it would be easy enough to just make one here, but use exclamation mark equals when you want not equals to. Right? Now, just because some of your answers are going to be not equal to something, and you're trying to say, I can't find a key, well, you remember it's exclamation mark equals is what you would write if you want to write the not equals to symbol. Maybe next generation they'll have a button, you know, over here that you could do it. Strange that they don't, but well, it is what it is. All right, let's look at the next story. Professional tennis player Martina Navratilova, got it the second time, Monica Seles, Rafael Nadal, John McEnroe, and Jimmy Connors are all left-handed. Did you know that? Because I didn't. Define the parameter P to be the proportion of professional tennis players, current and retired, who are left-handed. Researchers are interested in the hypothesis that it's bigger than 0.10, right? Now, do you notice they have told me the alternate hypothesis? Now, what's the population of interest? Wouldn't it be all the ones up there? Write the hypothesis in words, being careful to specify. So what we're trying to do here, our researchers are interested in the hypothesis that the proportion of current retired professional tennis players who are left-handed is greater than that number. Okay, that's basically the sentence, right? So we're not calling it H, not an HA, but essentially that's the alternate HA. Here's some better ones. Just basic number practicing now. For each of the following, write down what the alternate would be. And do you see the key phrase? So the null is P is 0.2. Won't the alternate be P not equal to? That's how you write not equals. 0.2. Are you happy about that? Now, if it was a right-handed test, wouldn't this change? Well, let's pretend this one, right? Okay, I'm not liking this. Let me get the answers first and then criticize the book. That's 0.5. And that's 0.3. If this is the null hypothesis, how does that the alternate? And if this is the null hypothesis, can you see why that's the alternate? Isn't the alternate the opposite of what the null is? So let me criticize them. Maybe they didn't mean that. Do you notice how they've got a less than or equal to here, and they have a greater than or equal to here? Shouldn't a null hypothesis only have equals? Right, so pretend it says equals even if they don't. I think the reason they did this is so that it would be obvious what that is. But couldn't they have just made this equal and then said right-handed or left-handed, and you would have figured it out yourself? Oh, here's one in English. State the null and alternate hypothesis for each of the following potential research questions. In each question, also indicate whether the hypothesis test will be one-sided or two-sided. Okay. So here's the question. Will an increase in speed limits on the interstate highways lead to an increase in highway fatalities? So right now you've got a certain percentage, whatever it is, highway fatalities, right? And will it increase them or not? So the null hypothesis is no change, right? You increase the speed limits, no change. And the alternate would be that it would increase. So I want an H naught to be nothing happens and an alternate to be it increases. And I'm picking this one. Right, let's look at that one. Can you see it's got all the features I want? Isn't the null hypothesis increasing the speed limits does not change the fatality rate, right? The null hypothesis, nothing happens. And isn't the alternate then that it increases it? Is that test that I've just done, would that count as a one or two-sided test?
One-sided.
Right. It would have been better if they gave three options. Wouldn't it be better if they said right, left, and two, right? But one-sided it is. When the coin is spun on its edge, the probability that it will land up equal to 0.4. Okay. Now, won't the null hypothesis be that it is 0.5? What would the alternate be? Well, what's the opposite of it not being 0.5? Or let's face it, I just said the answer, didn't I? What's the opposite of it being 0.5? Right, not being 0.5. So the probability is 0.5 that the coin spun says its head is up. There we go. And won't this one be a two-sided? Because couldn't it be that the coin is more or less? I've just had two flickers on my light there. So usual, if it dies, unless it dies in the last 5 minutes, in which case class is over, give me 5 minutes to come back in. And if I don't, then my power's gone. Okay, let's try and create. Excuse me. Suppose that the present rate of success in a treatment of a particular psychiatric disorder for the relevant population is known to be 0.59. So they got a success rate in this of 59%. A research group hopes to demonstrate that the success rate of a new treatment is better than that. So if you're looking at this, won't the null hypothesis be that the new treatment is still 0.59, right? Nothing you see here, nothing's changed, right? You see where the 0.59 came from. Now, this one is an improvement. So wouldn't you hope to be able to prove that P is greater than 0.59? Oops. Are you happy how from this story, I was able to create these two guys. The null hypothesis will always be equals, regardless of what that bloody question up there said, right? Always equal. And the alternate will be bigger than this number, less than this number, or not equal to that number. Okay. Suppose a statistics teacher asked his students to each randomly pick a number from 0 to 7. His general theory is that the proportion who pick the number 0 will be less than what you would expect, right? Just by randomness. Use P to represent the population proportion that would pick the number 0. If it was truly random, wouldn't you get 1 out of 8? I'll do as a decimal. Because there's 8 numbers in that list, isn't it? And each one is just as likely as any of the others. And the null hypothesis is that one. Now, if you want to set this up, won't you say P is 0.125? There's nothing to see here. People pick 0 just as likely as to pick a 2. The alternate, based on what the professor suspects, can you see it there? Less than. So we are going to go P less than 0.125. Are we cool? Right, I want to do something for a few seconds. A very quick experiment. And you lot are going to take part as soon as I figure out where my buttons are. I'll write it down and then we'll do it. I don't want you to change your answer based on anything that's happened. I want you to just do what you would have done as if we hadn't done any questions. Right, there are 10 digits there, right? Let's look at them for a second. Off camera, I'm going to write down some predictions. Okay, I've now done it. So, looking at that, pick a number, pick a digit. Don't say it, just pick it. Have you all got your digit? I'm going to be starting in a few seconds from now. You all got a digit? Okay. Do that little hand thing, you know, unless I can physically see you. How many chose 0? Okay, one of you. How many choose 1? Interesting. How many choose 2? How many chose 3? Oh, 2, sorry. There we go. How many chose 3? How many chose 4? You have to put your hand down if you've already picked, because I might end up picking you twice. So Robert, for instance. Well, he's giving me 2 hands now. Okay, so back to my question. How many did 4? Was I just what? How many choose 5? 1, 2, okay. How many choose 6? 1. How many choose 7? 1, 2, oops, 1, 2, we're getting clicks off 3. How many choose 8? Just 1. Lastly, how many chose 9? Interesting. Now, I made some predictions here. Let's see how many I got correct. I said the fewest would be 0, but actually it was 1 in 9. So I don't think I won that one. I said the most would be 7. Would you agree I won that one? And I said more people would choose an odd number than an even number. Let's find out. 1, 2, 3, 4, 5, 6 chose even. Oops, 6 chose even. And odd, nobody there. 2, 4, 5, 6, 7. And I was right about that one. Would you agree I was a near miss with 0? Robert was just being awkward because he can be, and chose 0. If Robert hadn't chosen 0, wouldn't I be right in all 3 predictions before we even did it? And that's because human beings, as much as you think, we are not random. Why do you like the number 7? I got that one right. I could have picked any of the
Because
numbers.
somebody told you it was a lucky number.
Somebody told you it was a lucky number, right? Agreed. But isn't that very likely to be a cultural thing? Couldn't 8 be lucky if you're Asian and 3 be lucky if you're Korean, or whatever? Russians, it might be 5. I don't know, right? Why do we like odd numbers more than we like even numbers?
In art, it's more pleasing.
There must be something about odds that just were more pleasing, for whatever better word. See, we are very bad at picking random. That's why you shouldn't pick random. Yeah, I just randomly picked some people. Do you know you didn't? Subconsciously, you picked people for hair color or height or something about them that made them stand out. That's why your brain chose them, right? You know, if you had 50 people and you said, randomly just pick 3 people and you said, oh, him, her, and him, right? That kind of thing. Do you know how unrandom that truly is? Even although you think it isn't. We are very biased creatures, right? We don't even know half the time the biases that we've got. Okay. Do you think null and alternate hypothesis are generally statements about populations, about the sample, or about both? From what we've talked about, what do you think null and alternate hypotheses are? Take that off.
I would say both.
I would agree with you. Let's see if they agree with both of us. Yes. Isn't it about the population? For sure, right? Is the population bigger or smaller? But don't we typically base our evidence on what the sample tells us? Like the sample I just did right now, wasn't that evidence that you like 7s more than you like other numbers? So I would agree. God, if I was a horse, you would have shot me by now. I've said that before. Where are we going with this one? Right, back to notes then. So right now, if I gave you a story, would you be comfortable about setting up the null and alternate hypothesis? Right. That's kind of what we've done so far. So let's move on a little bit on our list of things and talk about test statistic and verifying can you conduct the test. So let's assume that I believe that if we do the 10-digit thing, right? That I believe that the probability that you pick a number 7 is greater than 0.1. Now that would be my null hypothesis, agreed? And I've just said the wrong thing, let's try that again. That would be my alternate, right? Y.1, isn't there 10 digits here? 1 out of 10 chance, that's 0.1. So that's actually the probability you pick any number, including a 7. So what would the null hypothesis be in this story? The alternate is that the probability you pick a 7 is more than 0.1. What is the null hypothesis?
P equals 0.1.
Right. I know because I'm looking at it and you can't see it, or P greater than or equal to 0.1. Ignore that statement. They do give you that choice, so just leave it, right? So our next part of the stage would be to collect a test statistic. Well, I actually have a test statistic. It wasn't a very big sample, of course, but didn't I do a sample of this class and 3 of you liked the 7? And that was 3 out of, darn it, how many's in this class? Well, why don't you do attendance right now? Say your last name and I can use that to get sample size. Okay. Right, so I have 16 of you. And 3 out of 16 is my sample. And my sample is 0.1875. Would you agree that that is evidence that it's more than 0.1? Now, if we were doing this last week, wouldn't I actually set up a 99 maybe confidence interval and do, you know, the spread of values that you would get and hopefully prove that my answer was always bigger than 0.1, something like that. But that's not where we're going to go. We are going to get p-hat, and that is good. Now let's look at verify that you can conduct a test. There's a lot of things that you could do. Most of them they don't check, but we will do some of them. Let's do size of sample. In other words, what's n look like? Can you remember the 10 test? Let's do it on this. N times p, right? And n times 1 minus p. Shouldn't both of them be bigger than or equal to 10? Right, the 10 test. In this particular example, would you agree that if p-hat is this guy, essentially the people who said yes was 3 and the people who said no was the other 13. Didn't it work okay for this one, but it failed on the top one? So my sample is too small. So n times p-hat must be bigger than 10 and n times 1 minus p-hat must be bigger than 10. If that's not true, then if you fail that, don't do a hypothesis test. It ain't going to work. The numbers you get won't make any sense. It doesn't matter what they are. You've not got enough information to make a valid decision about anything. Let's be silly. If I wanted to figure out the percentage of people who were left-handed, and I decided to do my sample of 2 people, wouldn't I come up with the whole world is 100% left-handed, 50% of you are left-handed, or nobody is left-handed? Would you agree that there's just not enough information in asking 2 people anything? Well, actually, there's not enough information in asking 10 people anything, or 20 people if it splits the wrong way. You have to have at least 10 yeses and 10 nos. That's what NP, N1 minus P is about. Now, the second one is pretty obvious, but we'll put it in.
Professor, you're not sharing your paper.
Oh, darn it in space. Thank you. I thought I was. Am I sharing it now? Right. So there's the NP test, right? In this case, 3 said yes and 13 said no. So we weren't getting anywhere with that one, right? And I'm saying 13, yeah. Now, It has to be a fair and representative sample. From the population. Do you think you lot are a fair representative sample of college students? Yeah, I'll stop shaking your head. Yeah, you're pretty typical college students. Are you a fair representative sample of adults in Washington State? Probably not. There are not enough old people here, or young ones for that matter. Right. So doesn't it really matter what the population of interest is, whether a particular sample is okay or not, right? I'll try to phrase this one. How you asked the question. In other words, how this one was phrased. Now, I just asked you to pick your, you know, a random number. And I did say, don't pay attention to what happened in before. Do you think if I hadn't done the zero story before I took my sample, do you think that might have influenced some of you? So, yeah, I would be a little bit worried about 3. Definitely 1 fails, definitely 3 fails, and this one's probably an okay. But just one of them needs to fail and the whole thing, forget it, right? So if one of them's no good, the whole thing is no good. And that is us for today. So I will see you all tomorrow, where we'll continue with these. Bye-bye, and I'll see you then.